Hi everyone, this is Miss Rosita. We're looking at section 8 of chapter 1 today. That would be the applications and modeling. In other words, word problems. So I listed on the first slide here all the different types of word problems that are in this section. The first type, solve a right triangle, that really, honestly, it doesn't sound very much like a word problem because literally the directions are solve the right triangle. But the others seem like they're more of your wordy word problems. So what I did was basically go through, give you some examples of each one of these in this PowerPoint or video. Okay, so when it does say solve the triangle, that means that they want you to find all of the angles in the triangle, all three of them, as well as all three sides. That's what they mean by solve the triangle. Now, of course, they're going to have to give you some of the values. Okay, so I put other problems involving right triangles will be word problems. The problem must give you at least two facts, sides and angles, and then you'll be asked to find the additional side or angle. So if they say solve the triangle, they want all the sides, all the angles, all 6 values. Or if it's in the midst of a word problem, then you just need to find whatever side it is that they ask you for. There are also problems called angle of elevation and angle of depression. So if in the word problem they say, let's say you're standing at the top of some building looking down on the ground, and it says the angle of depression is 30 degrees. You have to remember to measure that from horizontally across. So if you picture looking straight out on the horizon and then looking down by 30 degrees, it would be that angle that's swept out from horizontal down. Sometimes people will put the angle in the wrong place when they're drawing in their triangle, so you just have to be careful. Angle of elevation, likewise, if you're standing on the ground looking up at a tall building, then from horizontal up is going to be your angle that they're giving you. Okay, I put in an example with just a basic right triangle question. So it says we have a 100-foot line attached to a kite. And when the kite is has pulled the line taut, the angle of elevation to the kite is approximately 50 degrees. Approximate the height of the kite. Okay, well, first of all, a lot of times we'll use like this 100-foot line. When you see the word line, you want to be thinking of a rope or a string. And when the kite has pulled the line taut, that means now you have a line, literally, okay, like a geometry line, straight line. So anyway, the angle of elevation is 50. So in my picture here, imagine the kite at the top here, and it's on its string or its line all the way down here 100 feet, and at the bottom there's somebody standing here holding the kite. And that person looks up at the kite. So from horizontal up is 50 degrees. That's our angle of elevation. Okay, we're trying to figure out how high off the ground the kite is. So that's going to be the side I labeled H. So when I think about it, I've got the opposite and the hypotenuse compared to my angle 50. Okay, opposite of angle 50 and the hypotenuse. So that's going to be our sine ratio. Sine of 50 degrees is H over 100. So I just solve for H by multiplying by 100 and I get an answer. Next would be the navigation and surveying questions, and those ones get a little bit tricky with how you draw them out. So here you can see where I've listed examples, north 30 degrees east. Well, if I'm saying north 30 degrees east, you have to picture standing in the middle, facing straight up to be north, and then tilting in the eastern direction by 30 degrees. So the angle that we're talking about is this angle right in here between facing straight up and off to the right. Okay, so 30 degrees. Now this notation, they're always going to give you a letter N or S standing for north or south first, and then they'll give you the angle, and then they're going to give you east or west, E or W. Okay, so remember when you're drawing your compass, straight up is north, straight down is south, off to the left is what we call west, and off to the right is the east. So for the next one, south 43 east, you picture facing south, straight down, and then tilting in the eastern direction. So the angle that's swept out is this one right in here where my cursor is, 43 degrees. And then finally the last one, south by 75 west. So again, picturing facing straight down, and then tilting in the western direction, which on our paper is to the left, and this angle is 75. Let's see, I also made a note here that the angle that they're giving you is always going to be an acute angle. If you take a look at that last one, the 75 degrees west, what if it was south 100 degrees west, where the angle was not acute, they give you it as 100. So picture facing south and tipping in the western direction by 100 degrees, you're no longer actually south, you're north. So that's why we don't use an angle that's more than 90, because then we're not really going south anymore. We actually would rather call it just north by 80 west, something like that, right? Okay, last thing on the page here is about units. And because we're doing these navigation and surveying problems, oftentimes they're about boats or airplanes, and we use units called knots to measure our speed. So, if you're driving a car down the freeway, here we would talk about miles per hour. But if you're driving a boat, we don't do miles per hour. We actually do nautical miles per hour. Let me move this out of the way. We would be looking at 1 nautical mile per hour. And then you think, well, what is a nautical mile? Is that any different than a normal mile on land? Well, yes, it is. On land, you think of a mile as 5280 feet. But when you're on the water, we measure a nautical mile in meters. And so here you can see 1852 meters per hour is a knot. So 1 nautical mile is 1852 meters. And when we take that per hour, we get a knot. It's not that you have to really memorize this. It's just a matter of sometimes when you're reading the word problems and you don't know what one of the words means, it can throw you off. So I just wanted to at least mention our units of knots here. Okay, let's see. So fire towers. So if we have 2 fire towers, they're 30 meters apart, Tower A being due west of Tower B. Okay, if you stop there for a second, due west means straight to the left. So A is to the left of B. This is a horizontal line. The distance between A and B is 30 kilometers. Okay, keep going. It says, a fire is spotted from the towers. The bearings from A and from B are north 76 east and north 34 west, respectively. Respectively means that the first letter, which was A, goes with the first bearing, and the second letter goes with the second bearing. So in my picture here, I went ahead at point A, I drew a little north, south, east, west compass on there, and I'm picturing from A going north 76 east. So if I'm facing straight up and then I tip to the right, which is the eastern direction, 76 degrees is where I'm at. Notice that the 76 degrees is not the interior angle. It's the exterior angle of the triangle there. So the interior would be the complement of 76. So if I do 90 minus 76, I get 14. So in my triangle, this angle here must be 14 over by A. From point B, I again did my little north, south, east, west compass, and here it gives a bearing north 34 west. So picture facing north, tipping in the western direction by 34 degrees. So again, the interior angle of the triangle at point B needs to be the complement of 34 degrees, which is 56. 90 minus 34 is 56. So again, I have now in my big triangle, I know how much angle A is, I know how much angle B is, and I know how far apart A and B are. So I'm looking for, it says, find the distance D of the fire from the line segment AB. We always know we measured the distance at a right angle, so this is going to be a perpendicular line, which makes 2 right triangles. So if I'm looking for this distance D, what I want to do is set up a couple equations. So on my triangle for the left triangle, I could say the tangent of 14 degrees is D over, well, it's not the whole thing 30, I'm going to call it X. So again, tangent of 14 equals D over X, X being just that bottom edge of that triangle. I wrote it on the top here. Okay. On the other side, the triangle over there, we said that angle was 56 degrees. So if I set it up as tangent of 56 is D over, well, the bottom there needs to be 30 minus X, since the whole way across was 30 and we already named the other piece X. What's left is 30 minus X. So again, my tangent function will be D over 30 minus X. I wrote that at the top also. At that point, I have 2 equations and 2 unknowns, and it becomes just an algebra problem solving my 2 equations, 2 unknowns. So what I chose to do was I took my second equation and got the x by itself, and I substituted that into the first equation for x. So replace the x in the first equation with that. But if you go ahead and simplify it all down, eventually you're going to get the d. I just did the dot, dot, dot. You can too on your notes, just because I wanted to save space on my slide. And we're focused on the trig now, not the algebra. So hopefully that's okay. Okay, harmonic motion. Well, anytime you have an object that is going up and down and up and down and up and down, we can describe it with either a sine wave or a cosine wave, and we say it has simple harmonic motion. So some examples you'll see would be you put a weight on the bottom of a spring, and then you pull that weight down and let it go. And the spring is going to bounce that weight up and down and up and down and up and down. And as time passes, its displacement is going up and then down and then up and then down. So that can be represented with either a sine wave or a cosine wave. And then we have waves, and it could be waves in the water like the tide going in and out, or it could be sound waves like radio waves, it could be tuning forks, it could be, you know, a string on your guitar that's been plucked and it's vibrating. All of those would be appropriate to show as simple harmonic motion. Okay, so the thing that can throw you with these is they just mix things up a little bit with the vocabulary. So whether I have sine or cosine, I know that I'm going to have it still as your coefficient A is like the amplitude sine, and then for whatever reason our book switches from B to using the letter W. But whatever the number is in front of T, we know that affects the period. 2 pi over that number is the period. Our frequency, we did see, I think, in one previous homework question, but the frequency is the reciprocal of the period. So I just flipped my fraction over to get the frequency. Maximum displacement is basically my amplitude. So if you think of my sine wave that I have graphed here first, the distance from the x-axis is getting bigger and then getting smaller and then 0 and then getting smaller and then bigger. So it's oscillating up and down and up and down. So if I'm looking at the displacement of my object, it's getting displaced as it moves away from the x-axis. As it comes back toward the x-axis, it's getting closer to its equilibrium point, and then it moves away from the x-axis again. So the furthest away that it gets is when it's at the top peak or the bottom peak. That's when its amplitude is A. So its maximum displacement is A. Works the same for cosine. So one thing I guess I wanted to make sure was clear is when you're doing these harmonic motion problems, you can write your answer in terms of a sine wave or a cosine wave, either way. However, usually one of them makes more sense than the other because it just works out easier. So I put at the bottom here my note that when time is 0, and keep in mind the x-axis is our time, our displacement is going on the y-axis. So if they say at time equals t equals 0, that the displacement is 0, then that means it's starting off at the origin. It's going to look like our sine wave. But if they don't say that at time 0 we're starting off at the origin, our displacement 0, they might say you have your maximum displacement when t is 0. Well, then we would think, oh, cosine wave would be easier to start with. Whichever one you pick, though, you can always do a horizontal shift to get to the other one. So it doesn't really matter which one you choose. They both can work. It's just a matter which one's a little easier. Okay, so we're at the practice problems. Please give them a try as always, and check with people in your table group to see if you got them right. Okay, thank you so much for listening.